Today we're going to be doing a cooling problem in section 9a, and we're going to see if we can solve it using our differential equations. Alright, the problem states that Newton's law of cooling states that the rate of change of temperature of a body submerged in a bath is proportional to the difference of the temperature between the body and the bath. If a kettle of 100 degree water cools to a temperature of 80 degrees in 30 minutes when placed in a room of constant temperature 25, what is the proportionality constant? How long will it take for the kettle to reach room temperature? Okay, so the first thing we have to do is we have to actually write our differential equation. In this case, we're going to let dA represent the rate at which the kettle cools, and dt represent the change in time over which it cools. The problem states that a proportionality constant, which is K, is proportional to the temperature of our kettle minus the temperature of the room, which in this case is 25. And here we have our differential equation, dA over dt equals 12 times A minus 25. Next, we're going to need to solve our equation so we can get the general solution. All right, we're going to do this by doing separation of constants. We're going to multiply dt to the opposite side, and we're going to divide A minus 25 to the other side, and we're going to end up with dA over A minus 25 equals K dt. Okay, now that we have that, now we need to integrate. Okay, what might help a little bit is if we rewrite this equation as 1 over A minus 25 times dA equals K dt. We see that if we integrate the inside of our A minus 25, that we will get the top of our fraction here. So we're going to go integrate. That allows us to use ln as our solution. So what we're going to end up with is the ln of the absolute value of A minus 25 equals K t, which is the derivative of dt, plus c. Okay, now that we have that, now we can now we need to get rid of our ln. The way we do this is we raise both sides to the e. All right, and we end up with A minus 25 equals E kt plus c. All right, now we can rewrite the right side of this equation to A minus 25 equals E to the kt times E to the c. All right, we're going to deem this function c1 here, and we're going to let c, big C, equal E to the c1. And we can now rewrite our function as A minus 25 equals big C E to the kt, and we'll bring the 25 to the other side. We end up with A equals big C E to the kt plus 25, and here we have the general form of our equation. All right, now with that being done, now we need to find a more specific form. We can do this when we look at our equation and see that our initial at times t equals 0, our kettle equals the temperature of our kettle is 100 degrees. So in this case, we're going to end up with 100, which is our A, and also the temperature of our kettle, equals C times E to the K times 0, which is our initial time, plus 25. So solving for this, we know that K times 0 is 0, and E to the 0 equals 1. So, and we can pull our 25 to the other side. So we're going to end up with C equals 75, which brings us to a more specific form of our equation, which is A equals 75 E to the kt plus 25. Now that we have that done, we need to find a proportionality constant, which means that we need to essentially solve for K. All right, so what we're going to do is we're going to use our other condition, which is our 80. Our 10. We know that the pot cools to 80 degrees in 30 minutes. Okay, so that fills in the rest of our the rest of our constants, which allows us to solve for K. So we know that A now equals 80, which equals 75 E. We're solving for K, and now this whole cooling process takes place over 30 minutes. So now we put 30 in there, plus 25. We're going to bring the 25 to the other side. We end up with 55 over 75. Oh, excuse me, sorry. We're going to just subtract now. So we're going to end up with 55 equals 75 E to the K times 30. All right. Now we're going to divide 75. We're going to end up with 55 over 75 equals E to the K times 30. Okay. Now to get rid of our E in this equation so we can solve for our K, we're gonna put both sides in ln. We're going to use ln on both sides. All right. That's going to get rid of our E. So we're going to end up with the ln of 55 over 75 equals K times 30. All right, we're going to divide 30 out, and we're going to end up with K equals the ln of 55 over 75 divided by 30. And that's going to be our K. Now, plugging that into our original equation, we're going to end up with A equals 75 E to the ln of 55 over 75. I know it's hard to read, but it's there. Over 30 times T plus 25. All right, so that solves our equation. We found our K. We found our specific equation. All right, so now we're going to do part B. So the part B states how long will it take for the kettle to reach room temperature. Now we have to keep in mind now that as time passes on, T will only get larger, and we can see that since T will only increase, the 75 times E, 75 times E to the ln 55 over 75 over 30 times T will only get larger. So the equation, and we also know that room temperature is 25. So we know that as this term gets larger, A can never equal 25. A can never equal 25. And we can also think that since this term itself is not a transient term, it will never go to 0 as T goes to infinity. So with that being said, we know that the kettle will never actually make it to room temperature. So that is my differential equation problem. I hope you like it.